हेलो राजीव जी, कैसे हैं आप? हाउ आर यू?
I'm fine, sister. How are you?
I'm good, I'm good. So, in the meantime, others are joining. I think let's give a quick revision or recap कि अभी तक क्या क्या पढ़ाया गया है. So, I think it will be good. I don't know, my laptop start creating some issues. Okay, so yeah. Okay, so we can start to have some a quick recap what has been taught till now. Am I audible? Hello.
Yes, you are.
Okay. So yeah. Mele, could you like mute your mic? Hello, Mele. Mele, could you mute your mic? Oh God. Anyways, so let's give a quick recap what has been taught so far without starting today's assignment. So we have started with what are semiconductor materials, what are intrinsic semiconductor, what are extrinsic semiconductors. We can see that intrinsic semiconductor are the purest form of semiconductor, and then there was a concept of Fermi level, and oh God, I think I have to remove him from the call. What should I do? Okay, yeah. So in the intrinsic semiconductor, we explain the concept like what are intrinsic, what are extrinsic. There is a vacancy of an electron in the covalent is called hole, and then what are the specific band gaps, and then the concept of Fermi energy for the intrinsic semiconductor. In the intrinsic semiconductor, the Fermi energy nearly lies in the middle of the valence band and the conduction band, if you can see here. Okay, then we introduced you to the law of mass action, which is I'll share this slide. This is a much PDF I prepared. I will share this with today's assignment solution. So there is a law of mass action which states that Np is equals to Ni square, and in the intrinsic semiconductor we can calculate the number of electron and holes by these equations. Okay, now the intrinsic carrier concentration is like the we know in intrinsic semiconductor N is equals to P. From here we have calculated the intrinsic carrier concentration, and the numerical comes directly from here. Then there is a concept of Fermi level in intrinsic semiconductor, and the equation comes as this, but if Nc is equals to Nv, the equation is this. Then there is intrinsic conductivity and its equation. You can go by this PDF I'll share. Energy band gap. Then there is a concept of extrinsic semiconductor. We classify it into two types, N type and P type. What is N type, what is P type, I very well explained. And then how does the Fermi level changes for the N type and P type semiconductor. Okay, and its dependence on temperature. And then there's this law of mass action, on which we have solved certain numericals in last few classes. And then there's this direct and indirect band gap semiconductors. Please go through it. If you have any confusion, feel free to email me what is direct band gap semiconductor and what is indirect band semiconductor and the difference in between them. Okay, and then drift current, the concept of drift current and diffusion current, the equations of them, and then there's Einstein relation, where the equation of it, and the Hall effect. So in the Hall effect, we know the final equation comes at EH equal to VH by D, the Hall coefficients and its applications. Okay, and then there are certain these devices where we have talked about the photodiode or the LEDs, or you can say the laser diode, and the variation of Fermi level with temperature in intrinsic semiconductor, and then there is the working of PN junction. The PN junction has been taught. Yeah. So PN junctions. Mele, could you mute your mic? Your mic is open. That's why I had to remove you from the call. Yeah. So then we introduce the concept of PN junctions. What are P-type semiconductor, N-type semiconductor? What happens when there is a PN junction? And then from where to where the electron transfer takes place? And then what is the forward bias PN junction? What is the reverse bias PN junction? And we show the temperature dependence, leakage current, and all this stuff. And then what are N-type, what are P-type, and conduction in N-type and P-type. What happens when we join a P-type and N-type? How does this diffusion or drift current comes into picture? And then there is a formation of junction and a depletion region, and how this electron flow takes place. Okay, and then this is a Venn diagram of a PN junction, and then there is a built-in potential or built-in electric field, and how this alignment of the Fermi level takes place. Okay, then under bias, what happened, that if there is a forward bias, that means if there is a negative voltage on N side which promotes diffusion of electron by decreasing the built-in junction potential, that means it will give the higher current. Under the reverse bias, we know that the positive voltage is on the N side, which inhibits the diffusion of the electron by increasing built-in junction potential. That means the lower current. This is a diagram for the equilibrium condition. This is a forward bias, and this is the reverse bias, and you can see the bending of the bends, and how the flow of the majority and minority carrier is taking place in presence of a forward bias and the reverse bias. And then forward bias, reverse bias, this curve is there, and then PN junction IB characteristics there, where this current and voltage relationship is I is equals to I naught e raised to EV by KT minus 1. And what is the voltage breakdown, and how what this curve actually tells us about. Forward bias current is exponentially increasing, and the reverse bias low leakage current, which is nearly is equals to I naught. Now ability of a PN junction to pass current is in only one direction is known as a rectifying behavior. We expect that it should pass current in the one direction only, it should not be bidirectional. Like, it's not right for every condition. Then there is the concept of Schottky junction. When a metal and semiconductor are brought into contact, there are two types of junction formed depending on the work function of the semiconductor, and its relation with the metal is Schottky junction. That means phi m is greater than phi of semiconductor. And ohmic junction, in ohmic junction phi m is less than phi of semiconductor. For example, consider a junction formed between a metal and an N-type semiconductor, as shown in the figure. This is phi n, this is chi n, this is the N-type semiconductor, this is the valence band, this is the conduction band, this is the Fermi level before contact. And then what happens? The Fermi level of the semiconductor is higher than the metal. Since the work function is lower, we know it very well, the metal semiconductor का Fermi level high होगा. Similar to a metal junction, when the metal and semiconductor junction is formed, the Fermi level must line up at equilibrium. Another way to look at this is that there are electrons in the conduction level of the semiconductor which can move to the empty energy states above the Fermi level of the metal. So this leaves a positive charge on the semiconductor side, and due to the excess electron, okay, are you following it up? This is the N-type, this valence band, metal and semiconductor before contact. Now it leaves a positive charge on the semiconductor side, and due to this excess electrons, a negative charge on the metal side. Now when this contact is formed in between two metals, the charge resides on the surface. This is due to the high electron density found in metals. So what happens as a result? On the other hand, when there is a contact forming in between a metal and a semiconductor due to the low charge density on the semiconductor, you consider it as a semiconductor, and this is a metal, this is a depletion region, and we know that there is a low charge density on a semiconductor. The electrons are removed not only from the surface but they also form that certain depth within the semiconductor. This leads to the formation of a depletion region within the semiconductor. Okay, and this is a B naught, which is developing as a result of this electric field which is generating due to this junction forming in between. So when a Schottky junction is formed between a metal and a semiconductor, the Fermi level lines up, and also positive potential is formed on the semiconductor side. Okay, and because the depletion region extends within a certain depth in a semiconductor, there is bending of energy. Bending of energy bends on the semiconductor side. This means that the energy bend up, going up from the N-type semiconductor to the metal as shown in the figure below. Okay, this is a Schottky junction. I just gave you a minor introduction. You can go by this, how we calculate the built-in potential and what is our work function. And then there is a concept of biasing, what happens in a forward bias and what happens in a reverse bias. You can go by these slides. I'll share all this with. So just to show melee, you join a little later. I have just shown this PDF where I have made a short like I have tried to merge a short recap of whatever class we have taken so far. It has talked about intrinsic, extrinsic semiconductor, their conductivity, energy gap, formulas, Fermi level, and then drift and diffusion current, law of mass actions, difference in direct and indirect semiconductor, and all this stuff. And then Einstein relation, Hall effect, its application, and then certain devices, photodiodes, LEDs, and laser diode, and all this, the variation of Fermi level. Then I explained about the PN junction, and since PN junction you have already joined. So this was a quick recap. This was a quick recap of the classes till week 4. So let's go to the assignment. We start solving the assignment. It will be better. So I don't need to introduce myself. I just want to tell you that this is a backup live link where you can find all the videos and assignment which we upload like on a weekly basis, that we take the classes. In case you are not able to attend a class, you can access it through this link and then download it from there. And this is a YouTube channel link. You can try to see the video over there, and the videos are also available in this drive. So let's move forward. So the question 1 today is that a silicon PN junction diode consists of a p-type region containing 5 cross 10 is to power 16 centimeter inverse cube acceptors, and n-type region containing 3 is to 10 is to power 16 centimeter cube inverse donors. What is the total bit of a depletion region in micrometer if the applied voltage is equal to 0.6 volt, given the relative permittivity and free space permittivity are 11.8 and 8.85 cross 10 is to the power minus 14 farad centimeter inverse. So, and for this you have a time of 3 minutes, and please type your answers in the chat box. It's 3:14. I'm giving you till 3:18. Whoever can solve this question, that's good. If not, then I'll show the solution. It's a formula based question directly. I just showed you a quick recap, and I also put it a question in the last assignment regarding the formula. And I think somebody was confused also in the plus and minus sign, and it got cleared out. So kindly try to solve this question and tell a plausible answer if you can. Okay, so I think only one people is there, and probably you are seeing the videos afterward, or you may know everything. So let me try to show you the answer. Uh, st-
Sir, it's wrong calculation. Only need time calculation.
okay, so you're doing it. Great, great, great.
Yeah.
Yeah, yeah, do it, do it.
Yes.
Yeah,
Okay,
let's.
sir. So that I know the formula, sir. It's 2 epsilon and VBI minus VA by Q 1 by ND upon 1 by N. This
Yeah,
is the formula.
yeah. You try to solve it. Mele, so now I'm trying to show the solution. Okay,
Yes, sir. Yes, yes.
okay. So if you can see it, that's good. Anyways, I'll be sharing this. Okay. So we know the depletion, the formula of the depletion region W is equals to 2 Ks epsilon naught by Q, Na plus Nd over Na Nd VBT Vi minus Va whole raised to 1 by 2. That means this is whole under root. Now the calculated BVL from the given data is 0.789. So if we put all the values here, that means 2 cross 11.8 cross 8.85 cross 10 to the minus 14 over 1.6 into 10 to the minus 19 coulomb, and these values, that means Na and Nd, which was given here, 5 into 10 to the power 16 and 3 into 10 to the power 16. That means the values comes like this, and if you solve them and take the under root of it, the W will come at 0.115 micrometer. That means the correct option is B, 0.115 micrometer. Okay. Yes. Let's go to the second question. Actually, in the starting 4 or 5 question, I put some numericals. It will help you to during your exam. Like there will be certain numericals, and the assignment also containing numericals of this type only. So there is a silicon junction diode maintained at room temperature under equilibrium condition has a p side doping of Na equal to 10 to the power 15 centimeter cube inverse and an n side doping of Nd equal to 10 to the power 16 centimeter cube inverse respectively. The value of built-in potential would be the intrinsic carrier concentration in silicon at 300 Kelvin is 10 is to the power 10 centimeter cube inverse. That means we have been given the value of Na and Nd, we have been given the intrinsic carrier concentration at a particular temperature. Now we have to calculate the value of built-in potential.
Sir, what is the value of KT by Q? Can I consider it 25 points?
Mm, I
KT by
think
Q.
yeah, KT in KT by Q we took the temperature as room temperature, right? The KT by
Yes.
Q, yeah, I think you can consider it.
Then 25.7.
Yeah, but this is around 298 Kelvin. So I mean, this here the temperature, the value is given at 300. You can consider it. The answer will come
Yes.
nearby. You give a try.
Sir, please show the. Okay, sir. Question.
Just a
Okay.
minute.
Yes, value I know.
Yeah.
Okay, sir.
Uh, Ganpesh, we are solving this question. Question number two.
Sir, what is the value of Na 10 to the power not visible?
Okay. Let me
Na and Nd, just tell me 10 to the power.
10 to the power 15 and 10 to the power 16, and
Okay.
the
And
built-in
it's 10 to the
potential
power 10.
and 10 to power 10. Yeah.
Okay,
So Ganpesh, we are solving this question. Question number two. It's a numerical and it can help you to solve the numerical in the assignment. The question is saying that there is a PN junction diode maintained at room temperature under equilibrium condition, which has p side doping of Na equal to 10 to the power 15 centimeter cube inverse and n side doping of Nd is equal to 10 to the power 16 centimeter cube inverse. So value of built-in potential will be what if the intrinsic carrier concentration in silicon at 300 Kelvin is 10 to the power 10 centimeter cube inverse. It's a direct formula based question. Give a try, and I'm giving you 3 minutes, 3 to 4 minutes to solve this question.
sir. Option D.
Okay, you give a try. That's nice.
Option.
Let's see. We
Yes,
will
sir.
discuss the solution. I'm not like reminding it, but we'll give you a solution. Shurikant,
Okay.
we are trying to solve this question number two. So in this question number two, Mele, now could you mute your mic? Yeah. So in question number two, we are trying to find out the built-in potential when we are given a p-side doping of Na equal to 10 raised to the power 15 centimeter cube inverse and n-side doping as 10 raised to the power 16 centimeter cube inverse, and this p-n junction is maintained at room temperature. Okay, so that means you can consider the value of kT by q as Mele was saying, I guess, and then we have to find out the built-in potential. So now I'm going to show you the answer, and this kind of question will definitely be there present in the assignments. So let's go to the answer. So we know that VBI is equals to KT by Q ln NA ND over NI square. So KT by Q is considered as 0.026 Mele. Okay,
Yes, sir. Yes.
and
Sir, actually, 10 square, na, I put it only 10 to the power 10, Ni square. That's why variation. Okay, sir.
okay, okay. But I am happy that you at least tried. That's good. So we know that KT by Q is 0.026 at room temperature. You can try to remind this value, and then ln. This is ln, okay, not log. This is ln. Remember this while you are solving. If you are putting it log, then you put it 2.303 along with this. Na nd over ni square. That means 10 is to the power 15 cross 10 is to the power 16 over 10 is to the power 10 ka square. So that means 10 is to the power 31 over 10 is to the power 20. 31 minus 20 will be 10 is to the power 11. 0.026 cross ln 10 is to the power 11. That means from the log table you can find out the value of this, and this is 25.328, and if you multiply it, that means you will get the answer as 0.658 volts. That means the correct answer is option B. Okay.
Yes. Sir, sir, one thing, sir.
Hmm.
Sir, sir, in final, sir, only objective type questions will come.
Yeah,
Final exam.
yeah, only objective type
Total
question.
based on objective and mathematics based on our like our assignments type.
Yeah, exactly. Only only objective
Okay,
type
sir.
questions will be there.
Okay, sir.
that
Thank you,
is
sir.
that is why you need to practice it like this, and i
Yes,
think
sir.
i
Yes,
think
sir.
these kind of question will be present in the assignment that have been there, right?
Sir, sir, what is the number of the final?
Yeah, like I have already sent a mail, and I'll confirm this. Like Rajiv sir also, like Rajiv ji also asked me about this missed exam thing, and like what is the total number, and can we do this, can we do that?
Yes.
I forgot in the last week, but I have already sent a mail. As soon as I'll get a reply, I'll inform, or in the next weekend class, or I'll send a mail personally. You can remind me in my email ID that what will be the total marks, and what are the weightage of the assignments that they are carrying. They were telling me that everything is mentioned on the website. I have not gone through it, but if it is not mentioned, I'll tell you. And if somebody has missed, then what is the procedure of giving the exam, I'll tell you. Okay.
Sir, and sir, questions will be prepared by our Ashish Garg, sir.
Yeah, yeah, you can
Or
say
maybe I don't know. Just
yeah,
I have no idea. This is my first time.
questions will be prepared by Ashish Garg sir, but we will be,
Ashish, sir.
yeah, but the question will be like this only, like the way we are solving. They will not be tougher than
Okay.
this. I'm assuring you this, and probably you can get a
Okay.
repetition of these kind of question with just the change values. That I am assuring you.
Okay.
Yeah.
Thank you, sir. Actually, we are working now, sir. That's why we don't have so much time. Only we are based on the assignments and sir's lecture.
That is why I'm
Only the
saying,
time. One,
if
two.
only
Yes,
that
sir.
thing, you can do, no, that you, if you keep on seeing the assignment and if you see the first lecture, that will be enough.
Yes, yes,
Enough.
yes. We
Like
left study at 2008.
yeah.
Okay. After that, we are going to study. After how many years?
So what do you do, Mele?
Sir, I am working at Larsen and Toubro.
Oh, great. So you what did you do in
Yes, sir.
studies?
Actually, sir, uh, sir, BTech electrical, sir, 2008 batch, 4 to 8.
Okay, okay, great.
Actually, I am planning to move, sir, our solar view business. That's why with the course, I will apply for our HR to transfer me. At now I am at OFC optical fiber, so move
Hmm.
optical fiber to solar.
Hmm.
That's why.
That's great. That's interesting to know. That's great.
Also,
So I think this course will definitely help you to like at least
yes,
stand the basics and plan accordingly. So yeah.
actually, sir. Yes. Okay.
Okay. So let's move to the next question of today. Question number 3, where this is saying like the starting 5 questions are numericals today. So I am just trying to improve your solving skills and show you that what kind of questions could be there. So there the homojunction diode is under forward bias condition with applied voltage of 0.5 volt. Now given doping concentration on both p and n side of diode is 10 is to the power 17 centimeter cube inverse, and intrinsic carrier concentration is this. What is the junction potential of the diode in volts? This is also a formula based question. Give a try. It's 3:32. I'm giving you 4 minutes. I'll tell the solution at 3:36 or 3:37.
Number A. Sorry, answer A.
Okay, great. सो राजीव जी एंड गणपेश जी, मैं आपको सोल्यूशन दिखाता हूँ एंड आई थिंक द आंसर इज़ राइट व्हाट यू सेड इफ आई रिमेंबर इट. Yeah, it's A only. So the solution is like this. If you can see, we know the V junction is equals to VVI minus VA. Now VVI, from this formula we know KT by Q is 0.026. We just put it the value, and the same formula was applied here. NA and ND was same. So NA and ND, if you put 10 raised to power 17 cos 10 raised to power 17 over 10 raised to power 10, that means BVI comes as 0.838 volt, which was which we were trying to find out here. Okay, our job was just to find BBI in the above question. Now when we have found out the BBI, now the V junction will be 0.838 minus 0.5, which was already given in the applied voltage. If you see the question, that means the applied voltage was given at 0.5 volt. So uh, if we calculate the V junction, that means VBI minus the applied voltage, that means 0.838 volt minus 0.5 volt, that is 0.338 volt. So the correct answer is A. Definitely. Very good, Male. So let's move to the next question. Question number 4. The question number 4 is saying the diffusion coefficients of electrons and holes in a semiconductor are 45.2 and 17.5 centimeters square per second inverse respectively, and the carrier lifetime for electrons are and holes are 0.01 and zero point 0.1 microseconds respectively. So what is the ratio of diffusion length of electron and holes in a semiconductor? Remember, we are trying to ask the ratio of diffusion length of electrons, d of electrons and d of holes in a semiconductor. This is also a formula based question directly. It has been taught in the class. So give a try. I'm giving you 4 minutes. I'll tell the solution at 3:40.
Sir, answer E.
Okay, good.
And power of dp by tau 1 by
Nice.
dp2 by tau 2.
Yeah, you approached it right. That's the actual approach. Ganpesh, you there?
Yes, sir. And
Okay, so are you facing some difficulty or you have not gone through the class? Okay, let me show you the solution. So as he
sir, this
said,
is my first lecture, so that's why I'm confused.
this is your first lecture. Hello? It's your first lecture.
Yes,
Okay, so Ganpesh, like I don't know, there is some communication gap from I guess the team. I have to take it very seriously now because this is the fourth week going on, and uh, okay. So in case we have missed the previous assignments, Ganpesh, so you can go by this link. I'm sharing this in the chat also. This is a drive link. Okay, I don't know how to copy it from here. This is a drive link. Yeah, this is a drive link. I'm sharing in the chat once more. You can go to the drive where you can find out the previous lectures, I mean the previous assignment solution and the recording of it, and the PDF also, along with some additional study matter that I have given. And this is my YouTube channel where also we have uploaded the videos. In case you want to see it, you can go through it, and I assure you, even if you have missed it, you just see the PDF solution and the classes of sir, and try to solve this question. You will be able to go through it. And the best website for the use if you want to learn something more from the engineering, physics, or you can say the electrical point of view, then this is a website which is best, and you can go by this website. Okay, Ganpesh, so try to cover it up by next week so that you will be on the same ground as others. Okay, so let me go to the solution of question number 5. As we know that we have to calculate the ratio of the diffusion length of electron and holes, and we know that ln over lp is equals to under root of dn tau 1 over dp tau p, where dn and tau 1 are this the diffusion coefficients of electron and holes. That means dn dp, and the carrier lifetimes we know 0.01 and 0.1 microsecond. That is also the tau n and tau p. We put it the values dn tau n 45.2 cross 0.01 over 17.5 over 0.1, took the under root of it, and the answer is 0.508. So the ln over np is 0.508. Okay, is it okay, Male?
Yes.
Yeah, I mean, see, this is a very straightforward question. Such questions will be there in the assignment and exam also. So I guess there will be few numericals, and these I think, not a big deal if you will get the question just by changing the values. So if you are not able to follow up, you do have a look over the assignment after the classes, and before the exam just go through the assignment. I think that will be enough. Okay, so I think I have already shown you the solution of question number 5. Still, let me show you the question number 5 is saying somebody is able to trying to join. Oh, okay. So question number 5 is saying which of the following represents the long base approximation for a p-n junction diode. Here Ln and Lp are the diffusion lengths of electron and holes respectively, and Xn and Xp are the ends of equilibrium depletion region on the N and P side of the diode. And the options are Xn is very less than Ln, and Xp is very less than Lp. Xn is very higher than Lp, and Xp is higher than Ln. Xn is higher than Ln, and Xp is higher than Lp. Xn is less than Lp, Xp is less than Ln. It's a very straight and simple question. What is the answer?
Already same, sir. B. B, sir.
Yeah, right. The answer is V. That is, we know that very well. This is the approximation for p-n junction diode, and we know it that in the ends of the equilibrium, when there is this depletion region forming, then this Xn should be the greater. It should be greater than the diffusion length of the p side, and the Xp should be greater than the diffusion length on the n side. This is the approximation that we consider for a p-n junction diode. So yes, the option is B. Okay, now let's move to the next question. Okay, so next question is just for clarifying your doubt. So the next question is just to see if anyone of you knows, and if not, then I just wanted to tell that what is the difference in between the direct and indirect band semiconductors. So Ganpesh, Melody, Rajiv ji, could you try to tell me something if you know it? What do you think? Like, if you're trying to approach this course, I think this is some basic thing that you should know. So that's why I put this question.
Sir, in direct band gap, sir. Okay. Direct band gap, the CB and EB maxima and minima are at the same position, but that's why when the photon absorptivity is higher in direct, because here it has to travel less path to enter covalent bond to valence bond. That absorption is high.
Okay.
The direct band, and in case of indirect band gap, sir, their maximum minima not coincide. That's why the photon has to travel not only one direction electric field and also phonon side. So that's why
you were saying it right. The basic definition is this only. I have already put this in the merge PDF, by the way, that I'll be sharing, and I have taken the answer from there only. So let me do it a full screen this time. So just to tell, so that the doubt will be more clear. In direct band semiconductors, we know that energy in a wave vector is shown like this, and as Mele was telling, this is lying in a coincidental position. We can see this is a balance gap, this is a k vector, and this is a valence band conduction band, and if it has to go, it will follow this trajectory. Now in indirect semiconductor, the band diagram energy and the wave vector is shown below. This is Eg and this is there, which is much higher. So we can say that in direct band gap semiconductor, the maximum of the valence band and the minimum of the conduction band, they are present at the same of k. Okay, but in indirect band gap semiconductor, the maximum of the valence band, just a minute, if I can put a hand, yeah, and the minimum of the conduction band present at a different value of k vector. Okay, that means the value at which the conduction band is present and the value at which the valence band is present, they are present at a different value of k, but in terms of physics, if I'm talking in terms of vector, and if in indirect, this is at the same position. Okay, this is more or less the same thing that Mele was telling. The few other differences are in direct band gap semiconductors, when an electron recombines with the hole, it emits their energy in terms of light. We know that when the electron is going above and then it is coming down again to recombine with the hole, completing the whole cycle, it emits the energy in terms of light. And in direct band semiconductors, when an electron, I think I have to write indirect here, yeah, I put it a space, in electron recombines with the hole, it emits their energy in terms of heat. So the major difference you can see, in direct it emits the energy in terms of light, and in indirect it emits in terms of heat. So from here we can see that when we have to design some semiconductor where we want to do some application related to light, that means we have to use something on direct, which has a direct band gap. Now the lifetime, if we talk about the recombination lifetime, the charge carrier is very less, but here it is more, because it is following a much more trajectory in order to recombine. Okay. And other differences are, they are mostly from the compound semiconductor, but they are elemental. Example is indium phosphide or gallium arsenide, but in case of indirect, this is germanium or
Sir, what is compound semiconductor?
compound semiconductor. Means this is not an elemental form, melee. That means you can see indium is element, phosphorus is element, but when you are combining them, okay, indium phosphide is a compound. Like, it's the basic difference between a compound and an element. Element is a purest form. Compound means indium and phosphorus reacted, there is a hybridization, then there is a rearrangement of their orbitals, rearrangement of their energy bands. This is a compound. So this is not a pure form. So gallium arsenide, indium phosphate, but here you can see this is just a germanium and silicon. So they are the elemental forms, and the band gaps are like this, you can see. And the direct band gap semiconductors are used to fabricate LEDs and laser diodes, and the indirect band gap semiconductors are used to fabricate diodes and transistors. So I think these differences are fair enough to tell you. Okay, now let's move to the next question. This is also a theoretical question. So it is saying which of the following is not applicable of Hall effect, है ना? And the options are: Hall effect gives the information about the sign of the charge carriers. Hall effect can be used to measure the drift velocity of the charge carriers, where Vd is equals to J over Nq. Third is saying strong magnetic fields can be measured by using Hall effect. Fourth is saying the mobility of the charge carrier can be measured by the conductivity of the material and Hall coefficient. And the fifth is saying Hall effect can be used to measure a number of charge carriers per unit volume. So this is a theoretical question.
Number 2 is not.
Why do you think so? What is the drift velocity formula? Okay, so let me show you the solution. This is just a theoretical question. I think it needs discussion, so let me show you. So I've taken this from there. We know the ratio of the Hall electric field to the product of current, density and magnetic induction is known as Hall coefficients, which is RH is equals to EH over JB. Now substituting the value of EH in equation this, we get EH over JB is equals to 1 over NQ. Now the Hall coefficient for N-type semiconductor is, where for electron Q is equals to minus E and N is equals to N, RH equal to minus 1 over NE. So Hall coefficient for N-type semiconductor is RH equal to 1 over rho E, and Hall coefficient is negative when the charge carriers are electrons and positive when the charge carriers are holes. Let me elaborate it some more. So if you, the PDF that I will be sharing, if you go by this PDF, you can see so we have gone through the Hall effect. The Hall effect statement say like it was discovered by E.H. Hall in 1879, and it is saying that when a magnetic field is applied perpendicular to the current carrying semiconductor, if you can see, if a magnetic field is applied perpendicular to the current carrying semiconductor between 2 points on the opposite side of the semiconductor in direction perpendicular to both current and magnetic field, this phenomenon is known as Hall effect. Now suppose let a current I is passed in the conductor along x-axis and magnetic field B is applied along the y-axis. Due to the magnetic field, the charge carrier experiences a force F which is perpendicular to the xy plane, that is along the z-axis. Now the direction of the force is given by Fleming's left hand rule. You know it very well. Due to the displacement of the charge carrier, some transverse field known as Hall electric field is developed across the two faces, where the magnetic deflection force will be QVDB and Hall electric deflection force will be QEH. We know it very well. So now if there is equilibrium condition, QVDB is equals to QEH and EH equal to VDB. Therefore the drift velocity will be VD is equals to, if we take it here, that means J over NQ, where N is the number of charge carriers per unit volume. So from equation 3 and 4, EH equal to J over NQB, then the Hall voltage BH at the equilibrium. At the equilibrium it will be EH equal to VH over D. Now we talk about the Hall coefficient. We know that the ratio is RH equal to EH over JB. This I have already explained when electron Q is equals to minus E and N equal to N in case of N type of semiconductors, and since for holes it will be Q equal to E and N equal to P. So it will be minus 1 over Ne, and for electrons, and for holes it will be 1 over Pe. So now the applications. Yes, the Hall effect gives the information about the sign of the charge carriers. We can see here, that is right. The Hall effect can be used to measure a drift velocity of the charge carrier Vd equal to J over Nq. Yes, it is also right. I think we have calculated it. And strong magnetic field can be measured by using Hall effects. Yes, definitely, because B, it is a result of B. When we are applying the magnetic field under an xy plane, then only this electric field is getting, and then there is a concept of drift velocity and electric field. The mobility of the charge carrier can be measured by the conductivity of material, definitely, and Hall effect can be used to measure the number of charge carriers per unit volume. Absolutely. That means, Melee, all the answers, like all the options were right. Are you getting me?
Yes, sir.
Okay. Now the next question.
Yes.
The next question is the forward bias diode current. The forward bias diode current is more of drift current than the diffusion current. It is predominantly the drift current, it is predominantly the diffusion current, or it is an equal combination of the drift and diffusion current. So I am giving you 2 minutes. You can turn up your pages, go through the notes, or try to think from the brain. What is the forward bias diode current? It is more of drift or more of diffusion, or an equal combination of both.
For drift and diffusion.
Okay, you are saying that it's an equal combination of drift and diffusion.
Diffusion maximum drift also there.
That is right, but you are saying it is an equal coefficient, not predominantly diffusion, right?
No, predominantly diffusion.
Okay,
Then
great.
option is C.
Okay, let's see. So you are absolutely right. The option 3 is the right answer. Just to
But sir, there must be some drift current, na?
Absolutely, predominantly means predominantly means more of diffusion current, but yeah, there is a presence of drift current. Predominant
Yes.
means this diffusion current is dominating over the drift current. Okay.
Yes, sir,
So
definitely.
yeah, it's very good. You're learning very well. So the drift current, we can say drift current is when electron and holes respond to an electric field. I have to explain Melee, right? Because others, when they will see the video, they should be able to understand. So I'm explaining the whole concept. The drift current is when the electron and hole respond to an electric field. Now hole moves in the direction of the electric field while electron moves opposite to the electric field. This occurs as long as there are carriers available. Okay. Now when does the diffusion current happen? Diffusion current, we know that by the definition of diffusion, when holes and electron move from the areas of their higher concentration, where they are majority carrier, to the areas of their lower concentration where they become minority carriers. This occurs until they are uniformly distributed throughout the semiconductor. When the diode is forward biased, drift current is present, but because diffusion current grows exponentially, it dominates. That means yes, there is a presence of drift current, but as the diffusion current grows exponentially, it is dominated. To explain more, there the difference is in the drift and diffusion current is uh, under the action of an electric field, it randomly start drifting toward or away the applied electric field depend on the nature. So the drift of charge carrier produce a drift current, but in a semiconductor it is due to the concentration gradient. For drift current, external electric field is essential, but diffusion the current external field is not required. Now it depends on the carrier concentration and external electric field, but it depends upon the rate of charge of carrier concentration per unit length. That means if we are giving a forward bias, that means we are giving some external stimuli, right? That means there will be predominantly diffusion current that will be present along with the drift current. So the option 3 was right, as been told by you. Now let's move to the next question. This is an interesting question. Okay, so the question is saying that a diode whose terminal characteristics are related as ID is equals to IS, EV over neta Vt minus 1 is biased at ID equal to 2 milliampere, is dynamic resistance is, where eta is given 2 and Vt is given 25 millivolt, and you are having 2 minutes to tell me the answer. 3 minutes I am giving you, 3:57. You can tell me the answer at 4. Give a try. It's a formula based direct question.
What is the dynamic resistance formula? For the answer,
it's given, no? You see, ID, and you know the formula, the resistance is there. ID is what? The dynamic current. From there you can find out the dynamic resistance formula. Okay, so I'm just giving you a trick. Suppose Mele, suppose you don't know certain term and there are numerical data coming. Okay, I'm just giving you a trick, that I followed in my entrance exam. Suppose I have read a concept and I am not able to solve the answer, like I have just forgotten a formula, or there is certain new term which is coming which I'm not gone through, but I'm familiar with the situation. Now what you have to do, you have to see that what are the values that are given and what is the formula that you know, or there is some equation that has been given, and what is the missing value that you can find out from there. Now you find out the missing value. Now after finding out the missing value, now you see what is being asked and what could be the possible formula which could give the certain answer. Then you try to solve it. Are you getting me? This is a trick for the numericals.
Yes.
So just see. Now you give a try. I'm going to tell you the answer.
Sir, it's 12.5, right?
Okay, 12.5 ohm you're saying. Okay, let's see the answer. Yes, the answer is 25 ohm. You may have done a little mistake. So let's see. Given that I is 2 milliampere and we know that the voltage is 25, RD is equal to eta V over I. If you put the value, then I think you will get 25 ohm. Okay,
Sir, just sir, zoom it, sir. Yes. Okay, sir. Okay.
Okay. Okay, so let me show you the solution, like just for. So the concept is that the dynamic resistance can be defined from the IV characteristic, Mele. When
Yes,
a
sir.
diode is in a forward bias, now it is defined as a ratio of a small change to the voltage to a small change to the current. That means RD is equal to delta V over delta T, and delta V can be written as neta Vt over I. Now these all are the values that has been given, which you can even if you're good in mathematics, no, if you see this equation, you see this exponential sign, if you have read this graph theory, you would have been able to see visualize the graph from there. If you don't know, then still I have told you the answer. RD is equals to delta V over delta D. From here you can see this equation come, and it is the inverse of the slope of IV characteristic curve. Now in this equation we put it the values and the answer is 25 ohm. That means the correct answer was option number 1. Okay, now the second last question of today is that for every 10 degrees centigrade increase in temperature, the reverse saturation current of a PN junction will be increased by 10 times, 2 times, 4 times, or it remains the same. And I'm giving you 5 minutes to answer me.
Two times, sir.
Okay.
Because every 10 degree, every 10 degrees, reverse saturation current equals two times. Double.
Okay. So let's see. It is since it has this relation. So the answer is 2 times right. I have taken this question from a
I
website.
zero equals to some.
Yeah. So if you see this equation, I naught equal to AQ I NI square. If you omit it, that means I naught is directly proportional to NI square, and also NI square is equal to NC NV e raised to a minus EC by KT. That means what? That means this current and temperature. If you the reverse saturation current and temperature, if you see the relation, that means Ni equal to e raised to 1 minus Eg kT. The diode for which Eg by kT will be more, will have less number Ni, and subsequently will have less reverse saturation current. Now mathematically the reverse saturation current is I01 at the temperature T1 and I02 at the temperature T2. So I02 equal to I01 2 of T2 minus T1 over 10. That means this will be 2 times. Now what is the concept of reverse
Sir,
saturation current? Yeah.
sir, what is the A? A is the
A
area, sir.
A
Sir,
is a constant.
I not for me.
A is a constant.
Constant.
Yeah. It will be given to you. It depends on certain condition. The Q and I and these terms you know na, DP, LP, NP. Hello? Mele, you know these terms, right? D, LP, and NA and D?
Yes, sir.
Yeah, okay. So the concepts of reverse saturation current is it increases with an increase in temperature and rises 7% per degree centigrade for germanium silicon, and it approximately doubles for every 10 degrees Celsius rise in temperature. So yes, if a question comes like this, you just have to put 2 times directly. So let's move to the last question of today, and I would like to, this is also a theoretical question, this is not MCQ. I'm saying that prove that the Fermi level in intrinsic semiconductors always lie between the valence band and the conduction band. The question is, how will you prove that for the intrinsic semiconductor the Fermi level is always in between conduction band and valence band? First of all, do you agree with this statement? If you agree, then why do you think it will be in between? Mele, any guesses?
Sir, intrinsic semiconductor, sir, both side carrier concentration are same.
Yes, good. That means there will be no.
That's why, yes, sir. They will, if there is a extrinsic semiconductor, sir, if you're hoping, sir, the Fermi level will be high for
Okay. That means, yeah, it's
API
exactly.
safe.
Yeah, absolutely right. We know it. So yeah, if we go mathematically, so mathematically I wanted to show you for the intrinsic semiconductor both concentration are same. That means n equal to p, right, Mele? That means nc
Yes.
e raised to power minus ec by ef over kt equal to nv. If we move it here, that means np by nc equal to this. From there we get this equation, nv over nc equal to e over 2 ef minus ec plus ev over kt, where ec and ev are valence band and conduction band energy, and ef is a it's Fermi level, and kt we know k is a Boltzmann constant, t is a temperature. Now taking log on both the sides, log of nv over nc equal to 2 ef minus ec plus ev over kt. As we know, log base e raised to x equal to x. Now kt comes here, 2 ef minus ec plus ev. So 2ef is equals to ec plus ev plus kt log nv by nc. So ef will be kt by 2 log of nc over nv plus ev plus ec by 2. Now if you assume that nc is equals to nv, that means number conduction band and the balance band are same. That means this term will cancel out, Melee. Right?
Yes, sir.
Right. That means this term will cancel out. That means EF equal to EC plus EV by 2. Thus, we can say
Yes.
that the Fermi level in an intrinsic semiconductor, it always lies between the valence band and the conduction band. Okay?
Sir, same formula is happening when the during intrinsic n-type or p-type conductor. This is EF minus KT ln by 2
Yeah, formula.
by
No, no. That they are the
NG.
extrinsic. They are the extrinsic semiconductor. No, N type and P type.
Extrinsic, yes.
Yeah, but there this NC and NV are different, right?
Different.
Yeah, so
Yes.
that
That's
is.
why they are cancelled out. Same.
Yeah, here it cancel out
Yes,
in
same.
intrinsic. Yeah, because NC
Yes,
and
same.
you only send me na that the conduction and the balance when the carriers will be same, right? In intrinsic, because they're not
Yes.
doping. So this is why it cancels out, because log of 1 is 0, right? Log base
Yes.
10
Log
1 0. So this will be
is 10.
0. So 0 plus this means EF equal to EC plus EB by 2. And you remember this equation for this extrinsic also. And I've added this in notes. Okay. This is all.
Extrinsic, I remember. Already for problem came on same. How
Yeah.
many Fermi level will close to
Yeah.
conduction band and
Yeah.
PK?
Great. This is the formula for the extrinsic P type, I guess. Yeah. See, here Fermi level is this, and for N type, you can see the Fermi level is this. So there is this bend bending also concept which was showing, and it depends on the temperature. Okay, temperature and the
Sir, one thing.
yeah.
Sir, if we increase the temperature in PN junction there, sir,
Hmm.
okay, there VOC also decrease, sir.
Yeah, it depends. It depends. Like
Yes.
yeah.
That shows a graph where that shows that VOC decreased.
Hmm.
But sir, during a diode, where is only no bias is applied, okay, sir?
Hmm.
When no bias is applied, sir, I increase the temperature. I'm talking about ISC.
Short circuit.
Suppose short circuit current.
Hmm.
Initially, suppose in a minus I-axis, it will go at a position. Now I increasing the temperature. ISC will be down. Suppose -1, now it's -2. What I can do is ISC is current increase or decrease?
Increase.
Increase.
Yes. See, you go to the value. You don't see mathematically that -1 and -2. That means it is increasing. You take the absolute value. Mathematically, -1 is greater than -2, right? But
Yes.
but this graph is going down. That means it is
Down.
Increasing.
Increase.
Okay. Yeah.
Okay.
Okay.
Thank you.
Okay. Then that's today. That's all for today. And if you have any doubt, feel free to email me. And let's meet the next week. And try to find out this issues related to this question. I'll who will be making the questions, how will be questions will be there, and all this stuff I'll tell you next week, surely. Okay.
Okay, sir.
Okay then, Male, see you. Take care.
Thank
Bye.
you.